The cosmos is an ocean of unanswered questions. We float on a tiny speck, surrounded by a darkness that holds secrets far beyond our current grasp. This journey ventures into the heart of that darkness to explore 25 of the most profound cosmic mysteries. These are not just curiosities, they are fundamental puzzles that challenge the very nature of reality, from the first moment of existence to the ultimate fate of everything. By the end, you will possess a new perspective on the universe and our place within its grand, enigmatic design. We will confront the invisible force tearing space apart and ask if time itself has an end. Which of these cosmic riddles do you find the most haunting? Our journey begins at the very beginning with the greatest origin story of all. The Big Bang is often pictured as a colossal explosion in space, but it was far stranger. It was the rapid emergence of space and time themselves from a state of unimaginable density and heat. While we can trace the universe's expansion back over 13.8 billion years, our understanding hits a wall at the 1-second mark. Before that first second elapsed, the cosmos was a realm where the familiar laws of physics ceased to apply. This initial chapter is the Planck epoch, a period so brief it defies human comprehension, where all the fundamental forces of nature were fused into a single, unified power. We have no theory that can describe the behavior of matter and energy under such extreme conditions. It is a complete blank in our cosmic timeline. Then, in a fraction of that first second, something extraordinary happened. A theoretical process called cosmic inflation suggests the universe underwent a faster-than-light expansion, ballooning from smaller than a proton to a vast, macroscopic size in an infinitesimal moment. This idea elegantly explains why the universe appears so uniform in all directions. But the mechanism that started and stopped this hyper-expansion remains one of physics' deepest puzzles. What triggered this incredible growth spurt? What was the universe like before it? These questions push at the absolute limits of our scientific knowledge, leaving the very first moment of existence as the ultimate, untold mystery. But that initial singularity is not the only ghost in the cosmic machine. A far more pervasive and tangible mystery surrounds us today, an invisible scaffold that holds the very fabric of the universe together. We call it dark matter. Its existence is not just a wild guess, it is a conclusion forced upon us by the universe's own behavior. Look at a spinning galaxy. Just as planets closer to the Sun orbit faster due to its stronger gravity, you would expect stars at the outer edges of a galaxy to move more slowly than those near the bright, central core. Yet when astronomers measure these rotations, they find something startling. The outer stars whip around at nearly the same speed as the inner ones. The only plausible explanation is that the galaxy is embedded within a massive, invisible halo of something, a substance that provides the extra gravitational pull to keep those fast-moving stars from flying off into the void. This unseen anchor is dark matter. We see its gravitational signature everywhere. It bends the path of light from distant galaxies in a phenomenon called gravitational lensing, creating distorted and magnified images that act as cosmic fingerprints for the invisible mass warping space. Through these observations, we have calculated that this mysterious substance makes up about 27% of the entire universe, far more than all the atoms and light that we can see. Yet, for all its overwhelming presence, it refuses to interact with light or ordinary matter in any way we can directly measure. We are surrounded by an ocean of something we cannot touch, see, or probe. What are these invisible particles? Are they vast clouds of ancient, undiscovered matter? Or could our understanding of gravity itself be fundamentally incomplete on cosmic scales? This ghostly grip is a constant reminder that most of the cosmos is made of stuff we do not yet understand. If dark matter's gravity provides the cosmic glue, then a far more bizarre force is aggressively pulling the universe apart at its seams. The story of dark energy begins with a discovery so shocking it upended a century of cosmological thought. For decades, astronomers believed the universe's expansion, set in motion by the Big Bang, was gradually slowing down. The collective gravity of all the galaxies, they reasoned, was acting like a cosmic brake, tugging on the fabric of space and steadily reducing its rate of growth. Then, in 1998, two independent teams of researchers made a landmark observation. By studying distant, dying stars known as Type 1, a supernova, which act as standard candles with a known intrinsic brightness, they could measure how much the universe had stretched as their light traveled to Earth. The results were not just surprising, they were revolutionary. The light from these ancient explosions was fainter than expected, meaning they were even farther away than their redshifts indicated. The universe was not slowing down at all. It was expanding at an accelerating rate. This was like tossing a ball into the air and watching it not only fail to fall back down, but shoot away from you faster and faster into the sky. Something was overpowering gravity's pull, a mysterious, repulsive force embedded within the vacuum of space itself. Physicists gave this unknown entity a name: dark energy. Calculations now show this enigmatic driver makes up a staggering 68% of the entire cosmos. It is the dominant component of the universe, yet its origin is arguably the greatest puzzle in modern physics. Is it a manifestation of Einstein's cosmological constant, a constant energy density filling space homogeneously, or is it a dynamic field, dubbed quintessence, that changes over time? Perhaps it signals a need to radically modify our laws of gravity. We simply do not know. This accelerating push dictates the ultimate fate of the cosmos, leading toward a cold, isolated end where distant galaxies vanish over the cosmic horizon, their light never to reach us again. The force that constitutes the majority of everything is a complete and utter mystery, a phantom pressure woven into the empty void. The phantom pressure of dark energy does not just accelerate galaxies away from us, it writes the final chapter for the entire cosmos. This ultimate destiny hinges on a single, critical question. Will the universe expand forever, or will it eventually reverse course and collapse? For much of the 20th century, the favored scenario was the Big Crunch. In this dramatic finale, the collective gravity of all matter would eventually overcome the initial momentum of the Big Bang. The expansion would slow to a halt, and then space would begin to contract. Galaxies would rush together, the background temperature of the universe would soar, and all structure would be compressed into an unimaginably hot, dense state, a potential mirror of the beginning. It was a cyclical, almost poetic vision of birth, death, and rebirth. The discovery of dark energy shattered that symmetry. The relentless, repulsive force of dark energy appears to be permanent and dominant, making a Big Crunch increasingly unlikely. Instead, the leading model now points toward a far more lonely and gradual end, known as the heat death or the Big Freeze. In this scenario, the acceleration continues unchecked. Over trillions of years, galaxies beyond our local group will be pushed beyond the cosmic horizon, their light forever too stretched and faint to ever reach us. The universe will become a vast, ever-darkening expanse. Stars will eventually burn through their fuel and die, one by one, until no new ones are born. Black holes will slowly evaporate over incomprehensible timescales. All activity, all structure, and all heat will dissipate into a uniform, frigid sea of leftover particles. The universe would reach a state of maximum entropy, a final, eternal equilibrium where no energy can be harnessed for work, and no further change is possible. Yet, this is not the final word. Cosmologists continue to debate the true nature of dark energy. If it is not a constant force but a dynamic field called quintessence, its repulsive strength could weaken over time, or even reverse into an attractive force, reviving the possibility of a Big Crunch. Alternatively, it could grow stronger, leading to a truly terrifying finale known as the Big Rip, where the accelerating expansion becomes so violent that it tears apart galaxies, solar systems, planets, and even atoms themselves in a final, catastrophic instant. The fate of everything, from the largest galaxy cluster to the smallest particle, rests on the identity of this mysterious energy that fills the empty void. Its secret will ultimately determine whether the cosmos meets a slow whisper or a sudden, violent tear. Even as dark energy pushes the cosmos apart on the largest scales, a specific, powerful force is pulling us in. Our Milky Way galaxy is not drifting aimlessly. It is racing through the intergalactic void at a breathtaking speed of over 1 million miles per hour. But we are not moving toward anything obvious, like a single brilliant galaxy. Instead, our motion, and that of thousands of other galaxies, points toward a mysterious, invisible concentration of mass that astronomers call the Great Attractor. This colossal gravitational anomaly lies in the direction of the Centaurus constellation, a cosmic siren whose song we cannot directly hear. Imagine a vast, unseen mountain range in the depths of space, its immense gravity creating a river of galaxies all flowing toward its hidden slopes. Our local group, the Virgo supercluster, all are caught in this immense cosmic current. The central challenge in solving this mystery is a frustrating one, known as the zone of avoidance. This is the dense, dusty plain of our own Milky Way galaxy, which lies directly between us and the Great Attractor. It acts like a thick cosmic fog bank, completely obscuring our optical view of what lies beyond. It is the ultimate blind spot in our map of the universe. For decades, this region was a complete blank, a no-go zone for traditional telescopes. How do you study something you cannot see? The answer lies in looking with different eyes. Astronomers have turned to instruments that can peer through the dust, using radio waves, X-rays, and infrared light to slowly map the hidden structures. These surveys have revealed that the Great Attractor is not a single, monstrous object, but likely the core of the Laniakea supercluster, a vast filament of galaxies of which our own Milky Way is just a remote suburb. Even this discovery, however, may not be the final answer. Our entire supercluster seems to be pulled towards something even larger and more distant, a titanic structure known as the Shapley Attractor. This suggests a cosmic hierarchy of pulls and pushes, a web of gravity where we are but a single thread in an unimaginably vast tapestry. The Great Attractor forces us to acknowledge that our place in the universe is dynamic, that we are part of a grand, gravitational dance whose lead partners are still hidden from our view. The gravitational pull of the Great Attractor shapes our cosmic journey, but a different kind of signal once reached out across the void, a fleeting whisper that seemed to speak not of gravity, but of intelligence. On August 15, 1977, a radio telescope at Ohio State University known as the Big Ear was performing its routine survey of the sky. A volunteer named Jerry Amon was reviewing the computer printouts days later, a long scroll of paper filled with columns of letters and numbers representing the signal strength. Most of the data was unremarkable, the usual cosmic static. Then his eye caught a sequence so extraordinary that he circled it in red pen and wrote one word beside it: "Wow." The sequence, 6 characters long, represented a narrowband radio signal that burst out of the background noise. It came from the direction of the constellation Sagittarius, lasted for 72 seconds, the exact duration the Big Ear could hold a fixed point in the sky, and then it vanished. This was not just any signal. It matched the precise profile astronomers predicted for a transmission of artificial, extraterrestrial origin. It was a powerful, focused burst on a frequency that natural cosmic objects do not typically emit. The sacred frequency of hydrogen, 1.42 GHz, a quiet channel in the radio spectrum considered a logical choice for any civilization trying to make contact. The search for an explanation began immediately. Was it a secret military transmission, a reflection off a piece of space debris, or a signal from a passing satellite? Every conventional source was systematically ruled out. The signal was never heard again, despite dozens of subsequent searches pointed at the same patch of sky. Its singular, brilliant appearance and its perfect characteristics have cemented its place as the most tantalizing candidate for an alien message in the history of the search for extraterrestrial intelligence, SETI. It remains a profound enigma, a one-time cosmic shout that has faded back into an endless silence. Was it a fleeting hello from a civilization that turned its transmitter away? Was it an astronomical phenomenon we simply do not yet understand? Or was it, for just 72 seconds, the proof we have always been listening for? A lonely signal lost in the interstellar dark. While the WOW signal was a singular, fleeting event, the cosmos is now known to be filled with similar but far more common cosmic shouts. These are fast radio bursts, or FRB. They are among the most energetic and perplexing phenomena ever detected. Imagine the entire energy output of our Sun over 80 years, released in a single, blinding flash of radio waves that lasts for just a few thousandths of a second. Then it is gone. These bursts travel across billions of light years, and when their dispersed radio waves are finally captured by our most sensitive telescopes, they tell a story of unimaginable violence occurring somewhere in the distant universe. The first one was discovered only in 2007, hidden in archival data from a radio telescope in Australia. Since then, we have detected hundreds of them. Some are one-off events, erupting from a random point in the sky and never repeating. Others are repeaters, flashing from the same source over and over again, but with no predictable schedule. This erratic behavior is a primary reason they are so difficult to pin down. Catching one is like trying to photograph a specific lightning bolt in a global thunderstorm, without knowing when or where the next strike will occur. So what cosmic engine could possibly produce such a brief yet catastrophic release of power? The list of suspects is as fascinating as it is varied. The leading candidates are magnetars, which are a type of neutron star with a magnetic field so intense it could erase a credit card from hundreds of thousands of miles away. Theorists suggest that starquakes on the surfaces of these ultra-dense objects, or sudden rearrangements of their unimaginably powerful magnetic fields, could be the trigger for an FRB. Other potential sources include the cataclysmic mergers of neutron stars, or matter falling into newly formed black holes. Yet, the sheer intensity and rapid nature of these bursts have pushed some scientists to consider a more speculative and thrilling possibility. Could some FRBs be the result of advanced alien technology? The idea is not as far-fetched as it might seem. An intelligently engineered device, perhaps a powerful interstellar beacon or the byproduct of massive light sail propulsion systems, could theoretically produce a signal that matches the profile of an FRB. While this remains a remote hypothesis, it is a testament to how truly bizarre these signals are. They are cosmic messages in a bottle, carrying information from the farthest reaches of space and time, yet we are only just beginning to learn how to read them. Each new burst captured offers another piece of the puzzle, a fleeting clue to the violent and mysterious events that shape our dynamic universe. Fast radio bursts are not the only cosmic anomalies that have sparked thoughts of otherworldly engineers. For years, astronomers have been tracking a star that behaves unlike any other in the sky, a star whose light flickers in a way that defies all convention. Officially catalogued as KIC 8462852, it is better known as Tabby's star, named after the astronomer Tabitha Boyajian who led its investigation. This star, slightly larger and hotter than our own Sun, lies over 1,000 light-years away in the constellation Cygnus. Its story begins with the Kepler Space Telescope, which spent years staring at one patch of the sky, meticulously measuring the tiny, rhythmic dips in starlight caused by orbiting planets passing in front of their suns. A planetary transit creates a predictable, symmetrical dimming pattern, like a moth fluttering past a lamp. But Tabby's star was different. Kepler's data revealed that its light did not dip in a gentle, repeating rhythm. Instead, it plummeted by enormous amounts, up to 22%, in chaotic, irregular, and asymmetrical plunges of darkness. This was not the signature of a neat, spherical planet. It was as if someone were throwing a chaotic assortment of shapes, some vast and solid, between the star and our telescopes. The strangeness did not end there. Long-term studies of archival photographic plates revealed that Tabby's star has also been undergoing a mysterious long-term dimming, fading significantly over the past century. This combination of deep, erratic dips and a century-long fade was unprecedented. When natural explanations like a swarm of comets or a recent planetary collision fell short of fully explaining the extreme data, a more speculative and thrilling idea emerged. Could we be witnessing the construction of a Dyson sphere, a colossal megastructure built by an advanced civilization to harness the entire energy output of its star? The concept captured the public imagination, painting a picture of a stellar engine so vast it would periodically block the star's light in these bizarre, unnatural patterns. The scientific community, however, responded with intense scrutiny. Follow-up observations across the electromagnetic spectrum revealed a critical clue. The dimming was more pronounced at shorter, bluer wavelengths than at longer, infrared ones. This is the telltale signature of fine dust. A solid megastructure made of metal or rock would block all wavelengths of light equally. Dust, however, allows longer infrared light to pass through more easily while scattering and blocking the shorter blue light. This evidence strongly points toward a natural, if incredibly exotic, explanation. The leading theory now suggests that Tabby's star is surrounded by a vast, chaotic cloud of dust and debris, perhaps the remnants of a shattered moon or a catastrophically destroyed planet. This cloud, uneven and clumpy, orbits the star in a way that creates those deep, irregular transits. The long-term dimming could be caused by a larger, more diffuse disk of dust slowly drifting inward. While the alien megastructure hypothesis was a captivating thought experiment, it was the process of investigating it that truly unlocked the mystery. Tabby's star did not reveal aliens, but it did reveal a new class of stellar behavior, a type of cosmic chaos we never knew existed. It stands as a powerful lesson in how the universe constantly surprises us, and how the most thrilling mysteries often lead not to little green men, but to entirely new chapters in our understanding of the cosmos. The hunt for cosmic anomalies is not confined to distant stars. Sometimes the mystery arrives in our own celestial backyard, delivered by robotic messengers we sent out ourselves. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s, were pioneers in the truest sense. After completing their primary missions to Jupiter and Saturn, they continued on trajectories that would carry them out of the solar system entirely, becoming humanity's first emissaries to the interstellar void. For decades, scientists at NASA, a jet propulsion laboratory, meticulously tracked their positions using the faint ping of their radio signals. Over time, a tiny, persistent discrepancy emerged in the data. Both spacecraft were experiencing a constant, sunward deceleration. It was an incredibly small force, just 10 billion times weaker than the pull of Earth's gravity, but it was undeniable and completely unexpected. This was the Pioneer anomaly. For years, this tiny tug defied explanation. Was it a sign of some unknown gravitational effect? Did it point to a flaw in our understanding of Einstein's theory of general relativity? Perhaps it was evidence of exotic dark matter exerting a subtle drag on the probes. The possibilities sent ripples of excitement through the physics community, suggesting we might be on the verge of a major discovery. The solution, however, turned out to be far more ordinary, yet no less brilliant in its unraveling. The culprit was not new physics, but simple, mundane heat. The Pioneer probes were powered by radioisotope thermoelectric generators, which produced significant heat as a byproduct of their nuclear decay. This heat had to be radiated away into space to keep the spacecraft's instruments functioning. Scientists realized that this thermal radiation was not perfectly symmetrical. A little more heat was being emitted from the back of the spacecraft than from the front. This created a tiny but constant recoil force, a photon pressure pushing back against the direction of travel, exactly like a very weak rocket engine. It was this minuscule push from the spacecraft's own warmth that was causing the mysterious deceleration. Once this thermal radiation pressure was accurately modeled and accounted for, the anomaly vanished. The Pioneer anomaly stands as a powerful lesson in scientific humility. It reminds us that before we invoke dark matter or rewrite the laws of physics, we must first check to see if our own creations are simply casting a shadow we failed to anticipate. Our own spacecraft eventually explained their anomalies, but a far stranger visitor arrived without any explanation at all. In October 2017, astronomers at the Pan-STARRS Observatory in Hawaii spotted a faint point of light moving at incredible speed. Its trajectory was unlike anything seen before, a hyperbolic path that screamed it was not from here. This was Oumuamua, the first confirmed interstellar object ever detected passing through our solar system. Its name, from Hawaiian, appropriately means a messenger from the distant past. The data revealed a visitor of profound and unsettling strangeness. First was its shape. By analyzing how its brightness changed dramatically as it tumbled through space, scientists deduced it was highly elongated, perhaps 10 times as long as it was wide. This cigar or pancake-like form is unlike any known asteroid or comet in our own system, where such extreme proportions are unheard of. Then came the true mystery, its motion. As Oumuamua sped away from the Sun, something was pushing it ever so slightly, giving it a small but definite extra kick. This is called non-gravitational acceleration. For comets, this is easily explained. Heat from the Sun vaporizes their icy surfaces, creating jets of gas that act like tiny rocket engines. The problem was, Oumuamua showed no visible signs of this activity. No surrounding cloud of gas or dust, no detectable coma or tail. It was as dark and inert as a rock, yet something was making it accelerate as if it were an icy comet. This paradox ignited a fierce scientific debate. Was it a rare type of asteroid, a shard of a shattered world from another star system? Or was it an exotic, ancient comet whose ices vaporized in a way that left no visible trace, perhaps through a crust of carbon-rich gunk that sealed the outgassing to just a few unseen jets? The object's unusual reflectivity, or albedo, added another layer of intrigue, suggesting a surface that was both dark and strangely metallic. The combination of its bizarre shape and its hidden acceleration mechanism led some, like Harvard astronomer Avi Loeb, to propose a more radical hypothesis. Could Oumuamua be a piece of alien technology, a discarded light sail or a derelict probe from another civilization? While this idea captured headlines, the majority of astronomers favor natural explanations, pointing out that we have only just begun to sample the population of interstellar objects. Oumuamua was a one-of-a-kind data point, a fleeting glimpse of the building blocks of other worlds. It passed by too quickly and was discovered too late for a detailed look, leaving its true nature an open question. It serves as a humbling reminder that our solar system is not an island, but part of a vast galactic exchange, and that the next strange rock tumbling from the void could rewrite our understanding of cosmic diversity. This profound silence leads us to one of the most unsettling questions in all of science. If the universe is so vast and ancient, teeming with billions of potentially habitable worlds, then where is everybody? This is the core of the Fermi paradox, a puzzle born from a casual lunchtime conversation in the 1950s. Physicist Enrico Fermi, while discussing the possibility of interstellar travel, pointed to the sky and asked a devastatingly simple question that still echoes today. The numbers seem to be overwhelmingly in favor of life. With an estimated 100 billion galaxies, each containing hundreds of billions of stars, and many of those stars hosting planets in the just right Goldilocks zone for liquid water. The cosmic lottery should have produced a winning ticket for intelligence countless times. Our own galaxy alone is over 13 billion years old, providing more than enough time for entire civilizations to rise, fall, and perhaps even colonize the entire Milky Way. Given these odds, the sky should be ablaze with the radio chatter of 1,000 different cultures, or crisscrossed by the vessels of ancient empires. Yet, when we listen, we are met with a profound and eerie silence. This contradiction between the high probability of alien existence and the complete absence of any observable evidence is the heart of the paradox. So what explains the Great Silence? One chilling possibility is the concept of the Great Filter. This theory suggests that the evolution of life from its basic beginnings to a spacefaring civilization requires passing through a series of nearly impossible challenges. The filter could be behind us, something we on Earth miraculously overcame. Perhaps the spontaneous origin of life itself is an astronomically rare fluke. Or the leap from simple single-celled organisms to complex multicellular life might be the universe's true bottleneck. If this is the case, we might truly be alone, the only conscious beings in a galaxy of silent, barren worlds. The more terrifying alternative is that the Great Filter lies ahead of us. There could be a predictable, unavoidable catastrophe that destroys every technologically advanced species before they can spread beyond their home system. This could be something intrinsic, like a tendency for civilizations to destroy themselves with their own technology, through nuclear war, engineered plagues, or runaway artificial intelligence. Or it could be an external threat, like a gamma-ray burst that periodically sterilizes entire regions of the galaxy. If this is true, then our own future may hold a silent, insurmountable wall. Other solutions are less apocalyptic but no less strange. The zoo hypothesis proposes that advanced civilizations are out there, and they are fully aware of us. They have chosen to place our world in a kind of cosmic quarantine, observing us from a distance as we develop, much like we observe animals in a protected wildlife preserve. They are waiting for us to reach a certain level of maturity or technological sophistication before making contact, a threshold we have not yet crossed. Alternatively, we might simply be looking in the wrong way or at the wrong time. Perhaps interstellar communication uses technologies we cannot yet conceive of, something far beyond radio waves. Or maybe spacefaring cultures are so advanced that our planet, our star, and our entire civilization are simply beneath their notice, as an ant hill is to a human walking through a forest. The silence is not empty. It is full of answers we are not yet equipped to understand. The profound silence of the cosmos is matched only by the absolute darkness of its most enigmatic objects. Black holes represent a fundamental crisis in our understanding of reality, a place where the universe's own rules seem to break down. This crisis is crystallized in the black hole information paradox, a conflict that pits two pillars of modern physics against each other in an irreconcilable duel. On one side stands Einstein's theory of general relativity, which describes gravity as the curvature of spacetime. According to this theory, the event horizon of a black hole is a point of no return. Anything that crosses this boundary, whether a star, a planet, or a book, is lost forever to the outside universe. The black hole retains only three properties: mass, electric charge, and spin. All other information about what fell in, the specific arrangement of particles that made up those objects, is seemingly erased from existence. This idea is encapsulated in the phrase, "Black holes have no hair," meaning they are bald of any detailed information. For decades, this was the accepted, if unsettling, picture. Then, quantum mechanics entered the stage. Quantum theory, which governs the world of the very small, is built on a fundamental principle: information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must be preserved in some form. If you were to burn a book, its ashes and smoke would still contain, in principle, the information needed to reconstruct every single word. The universe, according to quantum law, keeps perfect records. So what happens when a book falls into a black hole? Does the universe simply forget it ever existed? This is the paradox. If general relativity is correct, information is lost forever, violating a sacred rule of quantum mechanics. If quantum mechanics is correct, then information must somehow escape the black hole, contradicting Einstein's theory. For 50 years, this problem has stood as a monumental impasse. The potential resolution came from Stephen Hawking. He discovered that black holes are not completely black. They slowly emit radiation and evaporate over astronomical timescales. This Hawking radiation, however, was calculated to be purely thermal, a random and featureless glow. It carries no information about what fell in. So, if a black hole eventually evaporates completely, leaving behind only this random radiation, then the information about everything it ever consumed is truly and permanently lost. The universe's perfect ledger would have a page torn out and burned. Most physicists find this conclusion deeply unacceptable, believing the solution must lie in a deeper theory that unifies gravity and quantum mechanics. One leading idea is that the information is not lost inside the hole, but is somehow encoded on its two-dimensional event horizon, a concept known as the holographic principle. As matter falls in, its information is smeared like a fingerprint across the surface, and then slowly, painstakingly, imprinted back onto the escaping Hawking radiation over the black hole's immensely long life. It would be like burning a book, but having its entire text perfectly encoded in the seemingly random pattern of the heat and light given off by the flames. Another, more radical suggestion is that black holes do not have a true interior at all. The event horizon might be a fiery wall of energy, a cosmic shield that instantly obliterates anything that touches it, while preserving its information on the surface. This firewall idea, however, creates its own set of violent contradictions. The information paradox forces us to confront the very nature of reality. Is spacetime a smooth, continuous fabric as Einstein described, or is it made of discrete, quantum bits of information? The answer, hidden behind the veil of the event horizon, holds the key to a theory of everything. Even the faintest afterglow of creation holds secrets that unsettle our most cherished assumptions. We find this ghostly imprint in the cosmic microwave background, the oldest light in the universe. This radiation is the cooled remnant of the Big Bang's fireball, a snapshot of the cosmos when it was just 380,000 years old. For decades, it has been our ultimate proof of a homogeneous and isotropic universe, one that looks the same in every direction, with no center and no edge. This is the bedrock cosmological principle. But then we looked closer, and the map began to whisper of an anomaly so strange it was given a forbidding name, the axis of evil. This is not a malevolent force, but a statistical peculiarity that seems to align the universe's oldest structures with the plane of our own humble solar system. When scientists mapped the tiny temperature fluctuations in the cosmic background, the hot and cold spots that seeded all future galaxies, they expected to find a random, patternless distribution. Instead, they found that these fluctuations appear to be aligned along a particular axis, a kind of cosmic equator. Unbelievably, this axis seems to be correlated with the ecliptic, the plane in which Earth and the other planets orbit the Sun. It is as if the universe's grandest blueprint is subtly tilted toward our local astronomical address. The implications of this are staggering. If this alignment is real and not a statistical fluke, it suggests the universe has a preferred direction, a fundamental lopsidedness that violates the cosmological principle. Why would the grand design of the entire cosmos care about the orientation of our little solar system? It feels like a cosmic version of discovering that every country on Earth has arranged its capital cities to point toward your hometown. The most likely explanation is that this is a colossal coincidence, a trick of the data or an unaccounted-for systematic error. Perhaps the way we process the signal from our own galaxy's foreground dust is imprinting this false pattern. Yet, despite rigorous checks, the anomaly persists in the data from multiple missions. Could it be that the principle of universality is not absolute, that on the largest scales, the cosmos is subtly anisotropic? Or does this hint at something even deeper? A connection between the quantum fluctuations of the infant universe and the local geometry that formed billions of years later. The axis of evil confronts us with a humbling possibility that our place in the cosmos might not be entirely random, and that the universe's first light carries an unexpected and deeply puzzling signature of our own home. This ghostly imprint on the cosmic background is a paradox of vast scales, but a similar strangeness governs the smallest building blocks of reality. Two particles can be born together in a single event, their fates forever intertwined. Even if you separate them, sending one to the far side of the galaxy and the other to a lab on Earth, they remain mysteriously linked. This is quantum entanglement. Measure a property of one particle, like its spin, and you instantly know the spin of its partner, no matter the immense distance between them. It is as if the two particles share a single, unified existence. This phenomenon is not just a mathematical curiosity. It has been confirmed in countless rigorous experiments. Scientists have sent entangled photons through fiber optic cables under cities, and even between ground stations and satellites, verifying that the connection holds across hundreds of miles. The moment you observe one particle, its twin seems to snap into a corresponding state immediately, faster than any signal could travel between them. This is what Albert Einstein famously derided as spooky action at a distance, a phrase that perfectly captures the deep unease this idea provokes. How can information, or at least the determination of a state, appear to travel instantaneously? This seems to violate a core tenet of Einstein's own theory of relativity, which states that nothing, not even information, can travel faster than the speed of light. The universe, it seems, has a built-in connection that operates outside our everyday understanding of space and time. So what is really happening? One interpretation is that the particles are not actually sending a signal. Instead, their shared reality is a single, non-local system. The properties we measure were never truly separate to begin with, but were part of a unified whole that transcends the physical space between them. The universe, at its most fundamental level, might be deeply interconnected in a way that makes our concept of separate objects an illusion. This challenges our most basic assumptions about locality, the idea that objects are only influenced by their immediate surroundings. Entanglement suggests that the cosmos is woven together with invisible threads that ignore distance entirely. The implications ripple outward, touching the very nature of cause and effect. Does measuring one particle cause the other to change, or are both outcomes predetermined from the moment of their creation? The experiments seem to support the former, that the act of observation itself forces the outcome into existence for both partners. This spooky connection is not just a laboratory oddity. It is the foundation for emerging technologies like quantum computing and ultra-secure quantum encryption. It hints that the fabric of spacetime itself may be a secondary structure, emerging from a deeper, more entangled quantum reality. We are left to wonder if the separations we see are merely a veil, and that beneath it, the universe is a single, inseparable whole. This profound silence leads us to one of the most unsettling questions in all of science. If the universe is so vast and ancient, teeming with billions of potentially habitable worlds, then where is everybody? This is the core of the Fermi paradox, a puzzle born from a casual lunchtime conversation in the 1950s. Physicist Enrico Fermi, while discussing the possibility of interstellar travel, pointed to the sky and asked a devastatingly simple question that still echoes today. The numbers seem to be overwhelmingly in favor of life. With an estimated 100 billion galaxies, each containing hundreds of billions of stars, and many of those stars hosting planets in the just right Goldilocks zone for liquid water, the cosmic lottery should have produced a winning ticket for intelligence countless times. Our own galaxy alone is over 13 billion years old, providing more than enough time for entire civilizations to rise, fall, and perhaps even colonize the entire Milky Way. Given these odds, the sky should be ablaze with the radio chatter of 1,000 different cultures, or crisscrossed by the vessels of ancient empires. Yet, when we listen, we are met with a profound and eerie silence. This contradiction between the high probability of alien existence and the complete absence of any observable evidence is the heart of the paradox. So what explains the Great Silence? One chilling possibility is the concept of the Great Filter. This theory suggests that the evolution of life from its basic beginnings to a spacefaring civilization requires passing through a series of nearly impossible challenges. The filter could be behind us, something we on Earth miraculously overcame. Perhaps the spontaneous origin of life itself is an astronomically rare fluke. Or the leap from simple single-celled organisms to complex multicellular life might be the universe's true bottleneck. If this is the case, we might truly be alone, the only conscious beings in a galaxy of silent, barren worlds. The more terrifying alternative is that the Great Filter lies ahead of us. There could be a predictable, unavoidable catastrophe that destroys every technologically advanced species before they can spread beyond their home system. This could be something intrinsic, like a tendency for civilizations to destroy themselves with their own technology, through nuclear war, engineered plagues, or runaway artificial intelligence. Or it could be an external threat, like a gamma-ray burst that periodically sterilizes entire regions of the galaxy. If this is true, then our own future may hold a silent, insurmountable wall. Other solutions are less apocalyptic but no less strange. The zoo hypothesis proposes that advanced civilizations are out there, and they are fully aware of us. They have chosen to place our world in a kind of cosmic quarantine, observing us from a distance as we develop, much like we observe animals in a protected wildlife preserve. They are waiting for us to reach a certain level of maturity or technological sophistication before making contact, a threshold we have not yet crossed. Alternatively, we might simply be looking in the wrong way or at the wrong time. Perhaps interstellar communication uses technologies we cannot yet conceive of, something far beyond radio waves. Or maybe spacefaring cultures are so advanced that our planet, our star, and our entire civilization are simply beneath their notice, as an ant hill is to a human walking through a forest. The silence is not empty. It is full of answers we are not yet equipped to understand. The profound silence of the cosmos can make our own world feel like a singular refuge, but even our closest companion holds a secret from a more dynamic past. The Moon today is a geologically dead world, a silent sphere of rock and dust. Yet, locked within its ancient rocks is evidence of a far more active youth. Samples returned by the Apollo astronauts revealed a startling truth. Billions of years ago, the Moon generated a magnetic field nearly as powerful as the one that surrounds Earth today. This is profoundly puzzling. A global magnetic field is typically generated by a dynamo, a process requiring a liquid, electrically conductive core churning with convection currents. Earth's field is powered by the furious circulation of molten iron in its outer core. The Moon, however, is much smaller, and its core is believed to have cooled and solidified relatively quickly. How could such a small body sustain a planetary-scale magnetic shield for so long? The answer seems to lie in a more dramatic and turbulent lunar infancy. One compelling theory points to a phenomenon called precession. Imagine a spinning top wobbling slowly as it rotates. Early in its history, the Moon was much closer to Earth, and our planet's immense gravitational pull would have exerted a strong torque on the slightly oblong Moon, causing its spin axis to wobble or precess dramatically. This mechanical shaking could have violently sloshed the Moon's liquid core, stirring it like a cup of coffee being swirled vigorously. This forced motion could have powered a short-lived but intense dynamo, generating a strong magnetic field without the need for the internal heat that drives Earth's more stable version. Another theory invokes a more catastrophic origin. The ancient Moon was bombarded by massive asteroids, impacts so violent they scarred its surface with the giant basins we see today. Such a colossal impact would have delivered an enormous amount of energy, not just creating a crater but sending seismic shockwaves through the entire world. This global jolt could have triggered a massive upheaval in the lunar mantle, radically altering the flow of heat from the core. A sudden, drastic change in core cooling could have unleashed a surge of convection, briefly powering the magnetic dynamo in a single, powerful burst. Each major impact might have temporarily switched the Moon's magnetic shield on, only for it to fade until the next world-shattering collision. These theories paint a picture of a young Moon utterly unlike the serene companion we see today. It was a world being violently shaken and stirred, its interior churned by both the gentle, persistent tug of Earth and the sudden, hammer blow strikes from space. The evidence for its fleeting magnetic field is a ghostly remnant of that primordial chaos, a clue that even the most placid celestial bodies can have surprisingly tumultuous histories. What other secrets are locked within the silent, cratered face of our nearest neighbor? Far beyond the orbit of Neptune lies a frozen frontier, a cosmic junkyard of icy remnants left over from the solar system's birth. This is the Kuiper Belt, and for decades, our models predicted a smooth, gradual distribution of objects, with their numbers steadily increasing the farther out you go. Yet, when our telescopes finally peered deep into this distant realm, they found something completely unexpected. The population of these icy worlds does not continue to rise. Instead, it plummets. Around 50 astronomical units from the Sun, the Kuiper Belt simply ends in a dramatic and unexplained cliff. It is as if you were walking along a beach where the sand gets progressively deeper, only to find it drops off into a sheer, bottomless abyss. This sharp edge defies everything we thought we knew about how our planetary system formed. The prevailing nebular hypothesis suggests the protoplanetary disk of dust and gas that swirled around our infant sun should have thinned out gently with distance. There is no obvious reason for such a sudden, clean cutoff in the debris. So what carved this cliff at the edge of our cosmic backyard? One compelling theory points to the gravitational hand of a hidden architect. The hypothetical Planet 9, a world several times the mass of Earth thought to orbit far beyond Pluto, could be the invisible sculptor. Its immense gravity over billions of years could have shepherded the orbits of the most distant Kuiper Belt objects, either flinging them inward toward the Sun or hurling them out into interstellar space, leaving behind a stark and empty boundary. We see the gravitational fingerprints of this potential planet in the strange, clustered orbits of some extreme trans-Neptunian objects, but the world itself remains elusive. Another, more dramatic possibility involves a stellar intruder. In the solar system's chaotic early days, a passing star could have ventured close to our newborn family. The gravitational tides from this flyby would have been catastrophic, violently stripping away the outer reaches of the Kuiper Belt like a cosmic thief, and stealing a vast reservoir of primordial ice, leaving only the truncated belt we observe today. This stellar encounter would have been a brief, violent event in our system's youth, a ghost whose signature is etched into the emptiness we see now. Each explanation paints a different portrait of our solar system's history, one of a hidden giant still lurking in the dark, or a long-lost traumatic encounter with another sun. The Kuiper Belt Cliff is a silent monument to a story we are only just beginning to read. a stark reminder that even the frozen fringes of our own home hold profound and unresolved mysteries. This growing cosmic discord has a name: the Hubble tension. It is a fundamental conflict over a single, crucial number, the Hubble constant. This value describes how fast the universe is expanding today, the current rate at which galaxies are receding from one another. For decades, astronomers have pursued this number with two primary and seemingly reliable methods. The first, the cosmic distance ladder, uses a series of steps to measure the expansion rate in our local universe. It starts with pulsating stars called Cepheids variables in nearby galaxies, whose predictable brightness allows for precise distance measurements. By observing these stars and the brilliant, standard candle explosions of Type 1, a supernova in the same galaxies, scientists can calibrate distances and velocities to calculate a very precise present-day expansion rate. The result is a specific, robust number. But then we look back, way back, to the very infant universe. The second method uses the cosmic microwave background, the afterglow of the Big Bang. The precise patterns of hot and cold spots in this ancient light, mapped by satellites like Planck, allow cosmologists to run the universe's evolution forward in their models. They input the ingredients of the early cosmos: dark matter, dark energy, and ordinary matter. And the model predicts what the expansion rate should be today. This prediction yields a different, equally robust number. And here is the crisis: the two numbers do not agree. The local measurement suggests a universe expanding significantly faster than the pristine early universe data predicts. The difference is not a small, negligible error. It is a persistent and statistically significant gap that has only grown with more precise observations. It is as if you calculated how fast a car should be going based on the power of its engine and the slope of the road, only to look at the speedometer and find it is moving much, much faster. One of our most fundamental assumptions about the cosmos must be wrong. This tension is not just a minor calibration issue. It is a potential crack in the foundation of the standard model of cosmology. Perhaps dark energy is not a constant force but is evolving, growing stronger over time. Maybe dark matter interacts with itself or with normal matter in ways we have not yet accounted for. Or, most thrillingly, this could be our first direct hint of an entirely new type of particle or field that played a role in the universe's history. A relic from the first seconds of existence that is now subtly influencing the fabric of reality. The Hubble tension is a quiet but insistent alarm bell, telling us that the cosmos still holds profound surprises, and that our most cherished map of reality may need a fundamental redrawing. This relentless expansion of space forces us to confront a more intimate mystery: the very flow of time itself. We feel its passage in every heartbeat and every setting sun, yet its fundamental nature remains one of physics' deepest enigmas. Is time a real, physical dimension like the three dimensions of space? Or is it simply a persistent illusion created by our conscious minds? Our best theory of the large-scale universe, Einstein's general relativity, treats time as a fourth dimension, woven together with space into a single fabric called spacetime. In this view, the past, present, and future all exist simultaneously in a static, unchanging block. Your birth, your life, and your eventual end are all just fixed coordinates in this cosmic loaf, with no special now that moves. This is a profoundly strange idea, completely at odds with our lived experience. Why do we perceive a relentless, one-way flow from past to future if all moments are equally real? The most compelling clue comes from the second law of thermodynamics, which introduces the concept of entropy. Entropy is a measure of disorder, a count of the number of ways a system's components can be rearranged without changing its overall appearance. The law states that the total entropy of an isolated system always increases over time. A hot cup of coffee left on a table will cool down, its heat dispersing irreversibly into the cooler air. You can never see the heat spontaneously flow back from the air into the cup. reheating the coffee. This inevitable slide from order to disorder gives us the arrow of time. We remember the past, where entropy was lower, and we move into a future where it is higher. The universe itself began in a state of incredibly low entropy at the Big Bang, a highly ordered configuration that has been unraveling and becoming more disordered for over 13 billion years. This ever-increasing chaos is what drives the flow we perceive. Yet, this only explains the direction of time, not its fundamental reality. When we descend into the quantum realm, the equations that govern particles often work just as well with time running forward or backward. This suggests that at the most basic level of reality, time may not be fundamental at all. Some physicists, like those working on loop quantum gravity, propose that time is an emergent property, a collective illusion that arises from the complex interactions of countless quantum events, much like the temperature of a gas emerges from the frantic motion of its individual molecules. It is not a primary ingredient of the universe, but a consequence of something deeper. If this is true, then our deepest intuition about reality, the steady, forward march of time, might be the grandest illusion of all. Does time truly exist without a conscious observer to witness its effects? Or are we, the observers, the very source of its flow? The answer may lie in a theory that finally unites the quantum world with the cosmic stage of gravity, a theory that would reveal whether time is a stage or one of the actors upon it. The nature of time is not the only place where our perception of reality is challenged by scale. While the cosmos is a web of luminous filaments and galaxy clusters, it is also home to staggering emptiness. One of the most profound examples of this nothingness is the Boötes void, a spherical region of space so vast and desolate it defies easy explanation. Stretching an almost incomprehensible 330 million light-years across, this void is a cosmic desert on a scale that numbs the mind. If our Milky Way galaxy were placed at its center, our nearest major galactic neighbor, Andromeda, would still be well inside this emptiness, leaving us in near-total isolation. In a universe teeming with hundreds of billions of galaxies, this void contains only a few dozen, a hauntingly sparse collection in an ocean of darkness. How does such a colossal pocket of near-nothing come to be? The existence of the Boötes void is a direct challenge to our models of cosmic evolution. The prevailing theory of the universe's large-scale structure is built on the idea of inflation, those first moments of hyper-expansion that planted tiny quantum seeds. Over billions of years, gravity acted on these seeds, pulling matter into dense knots that became galaxy clusters and long, winding supercluster filaments. The spaces between these filaments are the cosmic voids, but the Boötes void is not just any empty space, it is a supervoid, an order of magnitude larger than standard models predict. Its sheer size suggests a level of underdensity that seems statistically unlikely, a cosmic lottery where the winning ticket was for almost nothing at all. One possibility is that several smaller voids have merged over time, their walls collapsing and dissolving to form one gigantic empty bubble. Another, more speculative idea is that it was carved out by the gravitational influence of something we cannot see. Perhaps a concentration of repulsive dark energy in the distant past that pushed matter away from this region. The few galaxies that do reside within the void are themselves mysterious. They tend to be isolated, often irregular in shape, as if starved of the galactic interactions that drive the evolution of their cousins in the crowded clusters. These lonely islands are natural laboratories for studying how galaxies develop in the most extreme isolation imaginable. The Boötes void forces us to confront the fact that the cosmos is not just defined by what is there, but by what is not. It is a monument to absence, a billion light-year-wide question mark that asks us how well we truly understand the architecture of everything. Our most precise predictions for the universe's first moments contain a stubborn flaw, a mismatch between what our equations demand and what the oldest stars reveal. This is the cosmological lithium problem. According to the well-established theory of Big Bang nucleosynthesis, the first atomic nuclei were forged in the fiery furnace of the universe's first 20 minutes. In that brief, seething cauldron, protons and neutrons collided and fused, creating the primordial ingredients for everything to come. Our models, which beautifully predict the observed cosmic abundances of hydrogen and helium with stunning accuracy, also forecast a specific, small amount of the next element in the chain, lithium-7. The math is clear and elegant, a triumph of modern cosmology. Yet, when astronomers point their telescopes at the most ancient stars in our galaxy, the stellar relics that formed from nearly pristine primordial gas, they find a glaring inconsistency. These ancient suns contain only about 1/3 of the lithium that our theories say should be there. It is as if a master chef followed a perfect recipe for a cosmic soup, but when we taste the leftovers from the first bowl, a key ingredient is missing. This is not a small accounting error. It is a fundamental deficit that challenges our picture of the universe's infancy. Where did the lithium go? Could our understanding of nuclear physics be incomplete under those extreme conditions? Perhaps unknown particles, like certain types of dark matter, interacted with the primordial plasma and destroyed the lithium as it formed. Or maybe the ancient stars themselves have been slowly destroying the lithium over billions of years, dragging it from their surfaces down into their hot interiors where it is fused into heavier elements. Each proposed solution seems to create new problems, upsetting other parts of our exquisitely balanced model. The lithium problem is a quiet but persistent crack in the foundation of Big Bang cosmology. A reminder that even our most successful theories might be hiding a crucial piece of the puzzle, one that could reshape our understanding of the universe's very first nuclear reactions. Even the quietest corners of the universe are not truly empty. According to quantum field theory, the vacuum of space is a seething, bubbling sea of potential. Virtual particles flicker in and out of existence in fleeting pairs, a quantum foam where energy is borrowed and repaid almost instantly. For an observer moving at a constant velocity, this vacuum appears calm and empty. But for someone undergoing constant acceleration, this serene void transforms into a warm bath of radiation. This is the Unruh effect, a startling prediction that links motion to temperature. An astronaut accelerating through the void at a constant rate would not find themselves in cold darkness. Instead, they would be surrounded by a glow of warm particles, a heat bath that emerges directly from their own motion. The vacuum itself would feel hot. This bizarre phenomenon occurs because the accelerating observer's horizon acts like a filter, preventing them from seeing the full, balanced structure of the quantum fields. What appears as a neutral vacuum to a stationary observer becomes a thermal soup of real particles to the one accelerating. The faster the acceleration, the hotter this phantom glow becomes. It is a profound demonstration that the very concept of a particle is not absolute, but depends entirely on one's state of motion. This strange connection between acceleration and heat finds its most dramatic echo at the edge of a black hole. Stephen Hawking realized that the immense gravitational pull at the event horizon is, in a quantum sense, a form of relentless acceleration. Just as the accelerating astronaut sees a warm vacuum, the black hole's event horizon should also generate a thermal glow. This is Hawking radiation. The intense gravity near the horizon can capture one of the virtual particle pairs, pulling the negative energy particle into the black hole while its positive energy partner escapes into space. To a distant observer, this escaping particle looks exactly like radiation emanating from the black hole itself. The black hole, in paying the energy cost for this creation, loses a tiny amount of its mass. Over astronomical timescales, this slow leakage of radiation causes the black hole to evaporate. The Unruh effect and Hawking radiation are two sides of the same profound coin, revealing that gravity, acceleration, and quantum theory are inextricably linked. They show us that our classical notions of empty space and absolute reality dissolve at the extremes, replaced by a shimmering, observer-dependent tapestry where even motion can conjure heat from the void. The very foundation of cosmology rests on dark matter's invisible grip, a ghostly scaffold thought to be essential for every galaxy's birth. Yet the cosmos, in its infinite capacity for surprise, has presented us with a profound contradiction, a galaxy that seems to defy this universal rule. NGC 1052 DF2 is a cosmic phantom, a diffuse, ghostly galaxy that stunned astronomers by appearing to contain almost no dark matter at all. This discovery sent shockwaves through the scientific community. How could a galaxy even exist without the very substance we believe holds all galaxies together? DF2 is a large, ultra-diffuse galaxy, a faint, wispy collection of stars so spread out you can practically see right through it. When researchers measured the motions of its star clusters, they expected to find the telltale signs of hidden mass, the rapid orbits that would reveal the presence of a massive dark matter halo. Instead, they found the clusters moving at a slow, sedate pace. The visible matter alone was enough to account for all the gravity they could measure. There was no missing mass, no invisible anchor. This was not just an anomaly, it was a direct challenge to our understanding. For decades, the standard model of galaxy formation argued that dark matter clumps first, creating gravitational wells that then pull in ordinary gas and dust, which eventually forms stars. The dark matter is the framework, the skeleton upon which the luminous galaxy is built. A galaxy without dark matter turns that sequence entirely on its head. It suggests that galaxies can form through other, more chaotic processes, perhaps through tidal interactions where gas is stripped away from larger galaxies, leaving behind a dark matter-free relic. The existence of such galaxies is a double-edged sword. On one hand, it seemingly refutes alternative theories of gravity like modified Newtonian dynamics, or MND, which propose that there is no dark matter and that gravity simply behaves differently on large scales. If MND were correct, every galaxy should show the same modified gravitational effects. Yet DF2 behaves exactly as Newton's laws predict with only its visible mass. This paradoxically strengthens the case for dark matter as a real, physical substance, one that can be present or absent. On the other hand, its existence creates a new puzzle. If dark matter is real and separable from normal matter, how did DF2 lose all of its dark halo? Was it torn away in a violent encounter with a massive neighbor billions of years ago? Did it form in a unique, dark matter-poor environment? The discovery forces a fundamental re-evaluation. We must now explain not only why dark matter is everywhere, but also how, on rare occasions, a galaxy can manage to live without it. This cosmic outlier is a powerful reminder that our models are always incomplete, and that the universe holds exceptions to every rule we dare to write. A ghostly chill permeates the oldest light in the universe, a cold spot so vast and profound it seems to defy the very randomness of creation. Within the faint glow of the cosmic microwave background, that baby picture of the cosmos, most temperature variations are small statistical ripples. But one region, located in the constellation Eridanus, is an anomalous cold patch stretching over 1 billion light-years across. This is not a mere blotch. It is a cosmic cavity of cold whose existence challenges our standard models. When scientists first confirmed its presence, the immediate question was whether it was simply a statistical fluke. After all, in a map of the entire sky, you would expect a few unusual pixels purely by chance. Yet, sophisticated analyses have repeatedly shown that the cold spot is too large and too cold to be easily explained away as a random fluctuation. Its probability of occurring naturally in our standard model of the universe is less than 1 in 200, a cosmic roll of the dice that seems to have landed on a nearly impossible number. This has forced astronomers to consider more dramatic, physical explanations for this colossal frigid zone. One leading theory proposes that the cold spot is not a feature imprinted at the dawn of time, but a shadow cast by a later structure. This idea suggests the spot is a supervoid, an immense and mostly empty region of space lying between us and the cosmic microwave background. According to general relativity, as light travels through such a vast underdensity, it must climb out of a gravitational well. In an expanding universe dominated by dark energy, this cosmic climb causes the light to lose energy, a phenomenon known as the integrated Sachs-Wolf effect. The light is stretched, its wavelength lengthened, making it appear colder and redder when we finally observe it. Think of a cyclist pedaling up a long, gentle hill that is simultaneously sinking beneath them, a draining effort that leaves them exhausted and slower on the other side. The problem is, to create a cold spot of this magnitude, the supervoid would need to be unimaginably large and profoundly empty, even by the standards of the Boötes void. Searches for such a colossal void in the foreground have found some underdense regions, but nothing quite massive enough to fully account for the profound cold we observe. The supervoid explanation fits part of the puzzle, but it seems to be missing several crucial pieces, leaving the depth of the chill unexplained. This failure of conventional answers has opened the door to a truly spectacular possibility, one that reaches beyond our single universe. Some cosmologists have proposed that the cold spot could be a cosmic bruise, the imprint of a collision between our universe and another bubble universe in the vast multiverse. The theory of eternal inflation suggests our universe is just one expanding bubble in a frothing, infinite meta-universe, where other bubbles are constantly inflating into existence. If another such bubble had collided with ours in the distant past, during its initial inflationary phase, the energy released in that collision would have left a distinct signature on the cosmic microwave background. The interaction would have drained energy from that particular region of our cosmos, creating a vast, cool spot in the aftermath. It would be like two soap bubbles gently nudging each other, with the area of contact becoming slightly distorted and cooler than the rest of the surface. While this is an exotic and difficult hypothesis to test, it represents a breathtaking prospect. The cold spot could potentially be our first empirical evidence for a reality beyond our own, a tangible fingerprint of a parallel cosmos brushing against ours in the first moments of everything. Whether a statistical ghost, an unimaginable emptiness, or a scar from a multiverse clash, this anomalous cold challenges us to look deeper into the cosmic background, searching for answers written in the faintest whispers of the dawn. Time itself may not be an endless river flowing toward a distant sea. Its final chapter is written in the fading energy of the cosmos, a conclusion theorized as the heat death. This is the ultimate state of maximum entropy, where the universe achieves a perfect and eternal equilibrium. Every star has long since burned out, every black hole has evaporated through Hawking radiation, and all matter is evenly distributed as a thin, cold soup of subatomic particles. The temperature across all of space approaches absolute zero, the point where all motion ceases. In this frozen, dark cosmos, no energy gradients remain, no work can be done, and no change is possible. Time, in any meaningful sense, loses its purpose. With no events to mark its passage, does it simply cease to exist? Yet this chilling finale is not the only possibility. Some models of dark energy suggest a more violent end, the Big Rip. If the repulsive force of dark energy grows stronger over time, it will eventually overcome all other forces. First, galaxy clusters would be torn apart, then individual galaxies. As the end nears, the fabric of spacetime itself would rupture. Stars and planets would be shredded, and finally, in the last infinitesimal instant, the very bonds holding atoms and atomic nuclei together would be severed. The universe would dissolve into a cloud of disconnected particles, ripped apart by the very vacuum of space. In this scenario, time ends abruptly with a final, catastrophic event. There is a third, more cyclical vision. Could our universe be just one phase in an endless cycle of birth, death, and rebirth? The conformal cyclic cosmology proposed by Roger Penrose suggests that in the far, far future, when the universe has expanded to near nothingness, its loss of structure and scale allows it to conformally reset, becoming mathematically identical to the high-energy, low-entropy state of a new Big Bang. In this view, the end of time in one aeon is merely the beginning of time in the next, an eternal return with no singular beginning and no final end. Our entire cosmic history, from the first star to the last black hole, would simply be one episode in an infinite series. This leads to the most profound question of all. Is time a fundamental property of the universe, or is it an emergent illusion, a side effect of the universe's decreasing order? If time is not fundamental, then its end is not an event in time, but a transition to a different state of reality altogether. A timeless, changeless existence that we, as creatures of time, cannot possibly comprehend. The end of time is not just about the last ticking clock, but about the ultimate nature of existence itself. These 25 cosmic riddles are not merely gaps in our knowledge, they are chasms that reveal the profound depth of our ignorance. From the first impossible moment of the Big Bang to the final, chilling possibility of time's end, we are surrounded by phantoms. Dark matter's invisible hand sculpts the galaxies, while dark energy's phantom push tears the cosmos apart. We are pulled by unseen attractors, whispered to by fleeting signals like the wow, and baffled by interstellar visitors and ghostly galaxies that defy the very rules we thought governed reality. We have confronted the spooky connection of quantum entanglement, the unsettling silence of the Fermi paradox, and the cold, hard truth that our most precise maps of the universe contain anomalies like the axis of evil and the deep chill of the cold spot. Each mystery, from the Pioneer anomaly to the Kuiper belt's sharp edge, from the missing lithium to the moon's lost magnetic field, is a humbling reminder that our understanding is a tiny island in a vast ocean of the unknown. Yet, this is not a cause for despair, but for wonder. The pursuit of these answers, the relentless human drive to look into the darkness and ask why, is the very engine of science. It is what transforms the cosmos from a static picture into a living, breathing story, one we are all a part of. We have journeyed to the horizon of human knowledge. Now we turn to you. Which of these cosmic mysteries haunts your thoughts the most? Share your choice in the comments below, and let's continue this grand conversation about the greatest story ever told.